Hi, my name is John Hottenroth, and I'm a Market Development Manager here at National Instruments with a specific focus area on non-destructive test and ultrasonic imaging. And today I wanted to show you how PXI can provide benefits for both industrial and medical applications that are using ultrasonic non-destructive testing techniques or ultrasonic imaging techniques. So first, I want to give you a high-level picture of the demo setup, and then we'll go specifically into the demo, and you'll be able to see the screen a little better. So I have a couple power supplies in my PXI chassis, and the power supplies are providing power for the high-voltage pulsar that I have external on the bench. Now, this pulsar was designed by Diagnostic Sonar, and they're a partner who we also worked with on the demonstration and the software that you're going to be viewing today. It's a 32-channel pulsar, and those 32 pulses are going to come out to our ultrasound transducer. This is a 128-channel array, but we only have it hooked up to 32 of the channels because that's what our pulsar is capable of in this case. We're going to be looking at a steel sample today, and the steel sample has a kind of V configuration of holes drilled in the side. So the holes are 1.5 millimeter diameter. And we're going to be looking and showing how we can actually see the holes in the steel sample. But the same technology can apply to carbon fiber composite or any of a number of other materials. And again, as I mentioned, the same technology applies for medical as well. So we're going to generate our high voltage pulses. It'll convert it into an ultrasound signal. It'll come into the material, reflect back, and then we're going to be receiving that same signal back on the 32 channels of the pulsar module, and that's going to be passed back through these cables to our FlexRIO module. Now, the FlexRIO module is really the core of the system, and what FlexRIO is it's something that combines interchangeable I/O with a user programmable FPGA. In this case, the I/O that we're using is a 32-channel simultaneous sampling ADC module. So it uses the Texas Instruments AFE 5801 front end, which gives us 12-bit resolution and 50 megasample per second sampling. Again, we're using 4 of those to give us the full 32 simultaneous channels. Now that front end also combines additional features like a programmable array to give us things like time variable gain, as well as filtering options, all built into the front end. So this is specifically designed for these types of applications. Now, once the data is acquired from the ADCs, it's going to go into the FPGA module, which is a module that basically combines a high-performance Vertex 5 FPGA from Xilinx and allows the user to actually define the functionality of that module, in this case to take data, perform additional processing, and that processing could be anything from fast Fourier transforms to peak detect to gating to filtering, or really any of a number of different algorithms that the user wants to define as well, and even triggering options. So the FPGA module basically takes the data from the adapter module and then also connects to the high throughput bus that we have in the PXI backplane. And the PXI backplane provides high throughput up to 800 megabytes per second if we're using PCI Express back to our host PC. So in this case, we're acquiring data, doing some initial processing, and then passing the data back to the computer or the embedded controller in this case for additional processing and display. All right, moving to our demo. We've created a LabVIEW interface, and so we've used LabVIEW to program basically what's happening both on the PC or on the host side, as well as what's happening inside the FPGA. And so we have the ability to configure various aspects of the array, including the number of elements, in this case the frequency, which we're using a 3.5 megahertz array, and a variety of other functions, acquisition parameters, the beamforming processing that we're actually going to be implementing to create the image, and then various characteristics of the display as well. So on the acquisition tab, I've selected my target configuration to be basically this steel sample that I showed you previously. And I'm going to select that target configuration. On the right side, I can see our cascade plot. So this is basically our 32 channels of the that we're acquiring, and we're basically seeing those in real time. Now when I move my array across the steel sample, we can see on those 32 channels that basically we can see that something's happening. So I'm just moving it back and forth, and I can see that we're receiving indicating some sort of discontinuity that we're receiving back from the ultrasound pulses that we're sending out. And obviously we need to see, or we need to perform additional signal processing to actually turn that into an image. And so we've done that, so we have the beamforming processing that actually allows us to view the holes in the steel sample, and we can see the configuration that we have. So the ultrasound pulses are coming from the left of our screen, and you can see that we have 1, 2, 3, 4, 5, 6 holes. Again, I mentioned they're 1.5 millimeter drilled holes in the side of the steel. I can actually normalize this to give us a little bit better resolution, and we can see that we even have the ability to look at the 3D image. And again, as I go across, we can view that that image in real time of the holes in the sample. We also have the ability to change configurations like adding or subtracting filtering. So I had the filter option enabled, or the high pass filter option enabled, and we can see the impact that has both on the image as well as how fast it's updating. And so one of the nice parts about an FPGA is that we can specifically move processing into, or add processing in the FPGA without actually impacting the performance of our application. Now I'm going to switch over to another configuration where we're looking at the full depth of the steel. Again, I'm going to select my configuration. It's going to take a moment for it to load and update the parameters. And then once I do that, I can see again, this is our full steel sample. So we have our front wall on the left. We can see again our 6 holes that are in the middle of the sample. And then we have the back wall here on the right. So what we're showing with this demo is really that the FlexRIO platform that combines the interchangeable I/O with the user programmable FPGA can be combined with software to give a lot of flexibility and customizability to really allow you to optimize for a variety of applications, both for industrial and medical applications. So I thank you for taking the time to watch this demonstration video. I hope you learned about how FlexRIO can combine interchangeable I/O to give us very high channel counts, and even the ability to scale to 64 or 128 or 256 channel arrays. Combining that with user-defined processing from filtering to gating to even beamforming processing that you may want to perform, and giving us really just a very flexible and customizable platform for a variety of different applications on both industrial and medical non-destructive test and ultrasonic imaging. Thank you.